So we're going to begin the conversation of advanced kinematics by discussing the phrase, when do you need different variables? That needs to be bigger. Let's try this. That's not bad. All right. When do you need to have different variables? Well, there's three rules here. There's two that are hard and fast, absolutely one that we've specifically already discussed, and then there's kind of an optional rule that we'll talk about here a little bit in a minute. So I'm going to do the second one first, because it's the one you know. When are you currently forced, you absolutely need a new set of variables, no options? Different accelerations, correct. So I'm going to put that one second for reasons. Different accelerations. And one of those accelerations can be 0. One of them can, what does it mean if acceleration is 0? Moving at a constant velocity. So yes, that can be a different set of variables in this case. Let's talk about number 1, because number 1 has also already been discussed, but we didn't discuss it specifically in this way. Let's call this, splitting variables. There we are. Imagine I have an object that I throw straight up in the air. Okay, one of the first numbers that are probably going to be given to you, which you're going to decide, then it's going to be set, is going to be like the initial velocity. So I might say the initial velocity, just making something up here, is 15 meters per second. And because I threw it in the air, one of the other 5 variables is definitely set. What is it? Gravity, correct. Negative g. By the way, assuming that ground is 0 and up is positive in this particular case. Now, you'll notice I don't have 3 variables yet. Technically, in kinematics, what you're doing is when you put that 3rd variable, that's kind of your question. That's kind of you asking, okay, what's going on with the others? For example, here is a very common question that I have asked. How far is it, or how high is it at its max height? But literally by telling you its max height, I've asked a question. I've decided one of these 3 variables. Which variable did I decide? Yeah. I basically, by saying max height, we decided that final velocity is 0. But really, that's me asking a question. And now I could do the rest of the math, and the math would do this. The math would tell me how long it takes to get to the top, and exactly how much change in position there would be to get to the top. But I wouldn't necessarily have to make that if that wasn't the question. If that was the question, obviously that's what you'd have to do. But I could do this. I could say, you know what, let's make t 2 seconds. What would I be asking? What potential questions might I be asking now?
What is the velocity after 2 seconds?
How fast is it going after 2 seconds? Or what else?
How far did it go?
Ooh, careful with how far, not quite.
Okay, what is the displacement?
What's the difference there?
Far is just like, there's no direction to it, but the displacement, you're going at a positive or negative.
And specifically, I chose these numbers because if you were using, what number do we round g to when doing the multiple choice?
10.
10. We round it to 10 when doing multiple choice. Use 9.8 on all problems. Always, whenever you do a calculation, use 9.8. But on problems, we always round it to 10 so that we can do math quickly in your head. So I should be able to give you this. Initial velocity is 1.5, and time is 2 seconds. How long should it take this object to get to the top of its path? You should be able to do this quickly in your head, concepts known. How long would it take to get to the top of its path? Not necessarily the 2 seconds here. How much, what does g tell you? What is that 10 meters per second? What does g actually mean?
Divide the velocity initial by the 10.
I'm going to say that a little bit differently, but you are right. That is how you mathematically do it. The correct answer here is 1.5. But what that 10 tells you is that tells you how much velocity is going to change every second. So how fast will this object be going after 1 second? 5. And it's not going to get a full other 10. It would take a half a second to get to the rest, and that's why you're technically dividing this whole thing up. Does that make sense-ish? So in 2 seconds, that means it's past the top, hit the top, and it's coming back down. So when you calculate an answer, will it be positive or negative if you were to put this in the math?
Positive.
Positive. How come?
Because your starting position is at the start.
because it will reference that right there.
Yeah.
Exactly how much it is changed, not necessarily how far it's going to go. As a matter of fact, there is in fact a time that I could put in here that I punch in all the calculations and it actually tells me the answer is 0. When would that be?
It's back at its starting point.
Actually, you should know the answer to this. When would that be? 3 seconds. Because it takes 1.5 seconds to get the top, it's going to take another 1.5 seconds to get right back where it is. And then if I threw this in the calculation, it would kind of be dumb, but it would tell me that this gets to 0. Finally, the last thing that I could do, instead of putting in velocity final is 0 or the time is 2 seconds, is let's say I threw this ball from a height, and a bunch of you have already done this, I throw this ball from a height of 1.2 meters. So I plug in a displacement of negative 1.2 meters. And what am I now asking the question of? How long in total was it up in the air? And how fast was it going when it hit the ground? So by doing this, you can kind of like just put the whole thing together. Now, I showed you guys another method. And the other method was kind of going back to where I started just a second ago. You could do this. And then again, what would that time be? That time would be the time to go up. And then what would you do if you wanted the whole time? Well, that's no big deal. You would just make a new set of variables to reference the time going down. So honestly, the second one time that you can't you split the variables is you choose. You can divide these variables however much the heck you want. The easiest was the one I just mentioned. You can divide the variables on the way up and the way down, but you just have to know what those times then mean. The times are not the total times, it's just the time to go up, the time to go down, and I need both of them added together if I want that total time. Does that make sense?
Yeah.
Okay, and again, we just showed just a second ago how you choose. You simply choose by changing what numbers get put in to these particular spots so that you can look at a particular section. Finally, and this last one is the main one we're going to be talking a little bit about today. We're actually not going to talk about the easiest problem that go with this today. We'll talk about that a little bit more tomorrow. We're going to look at a different method today. But the third one should kind of make sense if there are different objects in a problem. Now, this lesson today can be split up into 2 sections. I don't want it to accidentally all come together, okay? This is all very testable, okay? You have actually already done 1 and 2 a ton in here. We haven't done a ton of 3, but it's actually not that bad. You'll see that a little bit more tomorrow. The last half of today is going to be focused on a methodology and something that occurs every once in a while in physics, okay? That is not necessarily testable, except there's probably going to be a bonus associated with it. And I want to start to kind of put a seed now so that as it grows, we can be ready for it when we get to it in chapter 3. Okay? So here's the situation that we're going to look at. We're going to look at different objects, but don't necessarily put the different objects with this other thing. All right, here we go. Let's choose a different color. We've been using too much yellow.
Purple.
You want green or purple?
Green. Purple.
Let's see how purple shows up. Purple's not going to work, I don't think.
Purple.
It's just not. We'll do green for a little bit. Is that okay?
Yes, worse than purple.
Okay, we'll see what I can do for purple. Just hold your horses, all right? All right, so here's the situation, okay? You have a vehicle traveling down the road very, very quickly. Let's say they're traveling down the road at 90 miles an hour, okay? When they pass a particular sign, and behind that sign is a depopo. There's a copper. Right? Seeing them traveling 90 miles an hour, getting that whole buzz, takes off to go catch them up. Okay? Now, this is going to be a particular ruffian in this situation. They are not going to slow down the whole time. Try to catch me, copper. And the cop is going to start from rest, and they're going to slam on the acceleration, and they're going to accelerate the whole time. The question here is going to be, how long until the cop catches this person if they accelerate at 5 meters per second squared? All right. Now, first setup here is you got 2 different objects, so that means we have 2 different sets of variables. Let's start with the easy one. Let's start with the speeder. Now, I like to make columns on this. You can kind of organize this however you want, or you can organize this as little as you want to a certain degree, as long as the information is there. What is true about the motion of the speeder that probably very much matters to us? Constant. Correct. Now, I am going to show you that if you want to always use the 5 variables, you can for even a constant velocity. It can lead some students to make more mistakes than they intend to. So let me talk about this real quick. Just watch. You don't have to write this down. Okay. What is the initial velocity of the speeder? 90 miles an hour. Based on what we just told you, what is the final velocity of the speeder? 90 miles an hour. Okay. All right. And based on what I've told you, what is the acceleration of the speeder? 0 meters per second squared, because no, you're all right. Constant velocity. Now, the big problem that's the mistake here is that I have told you in the past that if you have 3 variables out of this set of 5, you can solve the problem. And so this leads people to go, oh, I have 3 variables, I can solve this problem. Except that's not 3 variables. That is literally just 1 variable. What does all of this really say? The velocity is a constant 90 miles an hour. Do I have 3 pieces of information here? No, I have 1. So if you want to do this, it's fine. It can be nice because that means you can always start the exact same setup always. I just want to make sure that you understand that me personally, I would probably just do this. My velocity is 90 miles an hour, and there's my time, and there's my delta x. And the reason why that makes sense is that what equation am I going to be using for constant velocity? You have 2 options. Either you could start here, the definition of velocity, or I've said a couple times, me personally, after kind of getting into this for a while, just doing a little bit of algebra here, I like to start on this second one. Start with whichever one you want. I'm going to be using this one today. It's totally up to you and your comfort level. But you can see how many variables are in this equation. Those 3 right there. Yes? All right. Now, since we are dealing with different objects here, one important thing to start to look at is that this time, there's not necessarily just one time. This is the time that the speeder is traveling. So we need to be careful with subscripts. And this is the displacement of the speeder. And now I'm done with the speeder because that's all the information I know. I knew how fast they were going, and that's pretty much it. So let's go over to Depopa. What's important about their motion? Acceleration, so therefore we do need to do the 5 variables in this case. Once again, I technically could put subscripts all the way down here because this is everything specifically to Depopa, but the main one I would focus on is the time and the delta x. We did this problem about, I don't know what it was. Probably way too long ago. I keep thinking of it like it's yesterday. It was probably my 3rd year of teaching, so like 15 years ago or whatever. But I talked about Depopa, and one kid just apparently took it upon themselves to always do sound effects whenever I did a problem. So he was just like, whoop, whoop. I was like, why is that the first noise that you would have? I know where Depopa are when they make that noise. That's not the one. All right, moving on. All right, so what do we know about Depopa?
Accelerating at 5 meters per second.
Accelerating at 5 meters per second squared. Correct.
Initial velocity is 0.
Initial velocity of 0. Do we know anything else? No, we don't. That's all we know. Now I'm going to stop it because you might make some arguments here in just a second, and you're kind of right. But let me just stop you right here. This is where the new thing comes up. If you don't have enough information on either side, what you're going to head into is what's known as just system of equations. Multiple equations, multiple unknowns. You would have seen this, of course, in math, looking something like this. Y equals 40x. Y equals, let's go 2.5x squared, what is y and what is x? Yes? And you could probably solve this system of equations relatively easily. Yes? The main thing that's difficult right now is the idea that we have to develop those equations in order to be able to do that. And that's what we're primarily going to focus on. Yes, I want you to do the math well, but the main thing we're going to be doing right now is focusing on how do we get those equations. So there will be problems tomorrow that are simpler than this. The ones that are simpler than this, you will know they're simpler than this because there's still two objects, but there's plenty of information on both sides that you could solve. Or, which has regularly happened to you in here, there's one thing that you can solve over here that will get plugged in over there, and you can solve everything completely fine, yes? So the thing that separates is not the fact that they're different objects. That's going to come up on your homework. It's the fact that you don't have enough information on either side, and then this launches this next step. The next step, if you don't have enough information on either side, is to start looking at relationships. The two main ones that are probably going to be are right down here with time and displacement. Now I'm starting very, very simply here because you might have already recognized what some of these are, but be wary when you're like, oh, this is easy, I can do it in my head. I'm trying to give steps for you to be able to follow when it's not quite as easy. So let's start with time. Okay, and looking at the picture, when did we start measuring the time? Both of their times. Yeah, right when they passed. Okay, and when are we going to stop the times? So, how should the relationship of their times compare? They should be equal, absolutely. So what I'm going to do is, I'm going to say, all right, the time of the speeder is equal to the time of DePopo, and I'll just call that t. That way, when I come over here and I start plugging in my variables, we'll go ahead and use purple. I can say this is equal to t, and this is equal to t. And while not always going to be the case, do they start at the same spot?
Yes.
To the end of the same spot?
Yes.
So in this particular case, then the displacement of the speeder will equal the displacement of DePopo and equal delta x. Now, technically, this started off with 4 unknowns. These 4. But we've already worked out the relationships down to just 2. And if you have 2 variables, what do you need to solve the 2 variables? Multiple equations. You have 2 variables, what do you need? What if I had 3 variables? What would I need? You need a number of equations equal to the number of variables. So if I have 2 unknowns, I need 2 equations. If, like in the future, I have 3 unknowns, then I'll simply need 3 equations. All right. So how do I figure out what those particular equations even are? Well, let's start in the simplest place to start, and that is with, actually, I'm getting ahead of myself. Before I get too far, should we probably leave it at miles an hour?
No.
So let's do a conversion real quick. What is the conversion? Miles an hour to meters a second. 2.25 goes with which one? The meters per second, the miles per hour. You should know this or have it quickly on hand.
Or miles per hour.
Because it's miles per hour. So dividing this out, I think it's 40 meters a second. So there's your quick conversion. Now, how many possible equations do I have for the left side? 1. Start there. You only have one option. Write it down. Delta x equals velocity times time. And I don't usually love you plugging in numbers, but this is hard enough as it is. So let's go ahead and plug in numbers. And the other thing that we're going to plug in is the actual variables in question. In this particular case, my displacement is, well, I just called it delta x. What's my velocity? 40 meters per second. And we call delta t, t. By doing this equation right here, what I have just done is I have identified the 2 unknowns. What are the two unknowns? What are the two things I don't know? Time and displacement. So now I come over to this set. And the problem with this set is there's not one option. How many options are there of equations to choose from? There's a total 4 possible equations you could use. So how do I pick the right one? Well, the one you have to pick has the two things that you know and the two variables that you're looking for. And I believe that is 4 variables, which make up every equation. What equation has those 4 variables? Out of curiosity, I told you this would probably happen, but let's actually go. Are you accidentally learning the kinematic equations, like memorizing?
Not good enough.
No.
It takes time.
Only that one. But the first one.
But I mean, like, that's the thing, right? Like, that's what I told you would probably happen. Slowly but surely, you'll accidentally memorize the ones that you're probably using the most often. What do you do with the rest of them? Have them written down close at hand so you can check and make sure you're good. Now, let's go ahead and plug in here. Yeah, very good. There we are. What's delta x? Well, that's just a variable, so I leave it alone. What's vi?
0.
So that cancels this entire thing out. What's a?
5.
And what's delta t? How many variables are in that equation? How many variables are in this equation? So now that you have 2 equations with the same 2 unknowns, what you have is a system of equations. And now you can solve that with what are your 2 methods to solve system of equations? Substitution and elimination. Now, substitution is most often what people go for. We will talk in this class when elimination is actually easier. Both are fun. You hate this? Why? Why? I'm sorry, then suck it up. My favorite thing about this subject is the student that always goes like, when am I ever going to use this? When am I ever going to use this? Now, in truth, we all know that that person just doesn't want to do it. It's not them actually asking the question. They just think that they're justified. And then they walk into this class and I go, here's quadratic equation. Here's system of equation. You go, son of a, there is a freaking reason why we know all this. And the answer is yes. And then, of course, you also get the student that just wants to be lazy. Like, when am I ever going to use this? And do you know what the meanest, sassiest answer I have ever given a student is? You won't. All right, that's a jerk move. And it was only appropriate because that person did nothing ever. But moving on. All right, so you've got 2 equations, which, if I'm not mistaken, look an awful lot like these right here. The only difference being you're not using y and x, you're using delta x and t, but you 100% can do this. Now, a couple things to remember. At this point in time, several of you are like, I have no idea what's going on. Okay. I get a little bit nervous when people get super emotional about stuff because what you have to be very wary of is your brain chemistry. If you let your emotions spike too often, what's going to happen is that your body's going to go into fight or flight. Body goes into fight or flight, okay, what's going to happen is that you will not be cognitively working anything out whatsoever. So the answer is, I don't know how to do this. And then it becomes a self-fulfilling prophecy. By letting your emotion get big and not actually doing anything, you won't learn anything past this point. And it doesn't matter how many times you slam your head into this wall. So, be very wary of this. To help you, hopefully with this process, I will remind you of what I said at the very beginning. I am not requiring this for this upcoming test. We are doing this because I will eventually require it. So slow your roll, settle whatever emotions you're having, stop trying to go blah, 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 and try to figure out what the next step is. So I'll remind you how we got to where we are because I think all of you can do this. Number 1, let's start with the easy thing there, okay? And that is, there were different objects. Since there were different objects, we did 2 different sets of variables. Everybody good there?
Yep.
Next, we chose the constant velocity set over here because we knew it was going at a constant velocity. And this set over here, we chose the 5 variable ones because it was accelerated. Everybody good there? Okay, we filled in what we knew. It was 90 miles an hour here, 0 meters per second, and 5 meters per second squared. I think everybody's golden there. Yes? Cool. This is where it starts to become a little bit troublesome. Okay? The first thing to do is to identify how you know you will have to launch into multiple equations, multiple unknowns. And that is, you don't have enough information to solve any one of them by themselves. Make sense? Usually on a test, you will. But if you don't, honestly, the correct way to do this is just trial and error. But what I shared with you is there's a really easy way to do that trial and error by starting with this side, because how many possible options are there? 1. So I wrote down that equation, and then I fill in what I knew. By filling in what I knew, this right here told me exactly what the 2 variables were that I had to have. Yes? So the way I chose my next equation was simply, I want every kinematic equation has 4 variables, so I chose the 2 that I know and the 2 variables in question. Everybody good? Last thing I'm going to point out here is this. Even when it comes to the bonus, literally the development of these equations, which I just discussed with you, is going to be 80–90% of the points. That's where physics comes in. Now, yes, I want you to be able to do this math. I'm going to go over this math in just a second. But as far as relative importance is concerned, the math is like the last 20% will figure this out. So how do I do this? Substitution or elimination. Substitution is by far the easiest in this particular case due to the fact that they are both already solved for x. Since they are both already solved for x, they are both equal to each other, which means this becomes 40 meters per second t is equal to, let's round that to 2.5, not round it, simplify it to 2.5 t squared. Now, watch here, because I'm going to show you the math that math would usually have you do. It's direct translation in physics over here, and why it's dumb in the simpler one afterwards. So don't write it down until we get to the simpler one. But here's what math would usually have you do. Math is usually going to tell you to take this one and subtract it on both sides so that you are equal to 0 right over here. It's then going to tell you to go ahead and factor out the delta t, and it's going to say, the reason why this is because there's 2 answers for t, and they're not wrong. But what is one of those answers for t? 0. Why does that make sense based on the problem that we've set up?
Because we started at that point for 0.
What we are asking math is, when is it at the same spot? Why are there 2 answers? Because there's 2 answers. The first time they were at the same spot was at the very beginning, at 0. Obviously, we don't care about that one. We already knew that one. So now we want the later time. Now, what could I have done to simplify this process much easier? Let's go back in the math real quick. Go back. No, keep going. Stop. Yeah, you're good. Okay. What simple thing could I do here to make my life that much easier? What's that?
Divide by 2.
Divide by t. Cancel. Cancel. And now you take 40 divided by 2.5 in order to get your t, and you'll end up with 16 seconds. You can. I'm going to talk about that in a second. But in this particular case, I only asked you how long before the po-po catch.
Oh, I forgot what you asked.
It's fair.
I just did it all.
So the answer would just be 16 seconds. Now, number one, you do have some completionists, but you are trying to save time. This was the next thing I was going to ask. As I was saying, okay, but there's 2 other questions that I could possibly ask in this case. The first question that I could have possibly asked is exactly what you were saying. How far do they go in this time? And that is essentially the same thing that you usually have to do in a system of equations, which is you usually have to find x and y. We don't always require that, so if you want to be efficient and just measure 1, do keep that in mind, but you're 100% right. If you want to find y and you already have x, what do? You just literally plug it in. Okay? So in this particular case here, it's the exact same thing. What do you do if you want x? You just plug it in. Now, even if it doesn't require it, it's not a bad idea to just take your calculator and do it anyway, because it's the best check to see if you did it right by simply plugging 16 in here and then also plugging 16 in here, because of course, what should you find about both numbers if you've done it right? they should be exactly the same in both spots. The other question that I could have asked, which is not part of system of equations, is how fast was DePopo going, of course, when they caught them? In which case, well, that's simple. Now that I have time in this particular spot, I have 3 variables, so use your correct kinematic equation and just solve for VF. Cool beans? All right, let's look at another one. Sweet, I love that. All right, I always get a little bit nervous with my pop culture references because I like a good pop culture reference. The problem is when students come in, I've got the same pop culture reference and eventually like fade out of the lexicon, and I feel really bad because I'm like talking about The Matrix and like I would never know what that movie is. I know some of you do, but not everybody. Okay, so if I say Jurassic World and Chris Pratt was the person defending against the Raptors, we cool with that ish?
Yes.
Cool. All right. So Chris Pratt, or whoever he played, I have no idea what his actual name was, so we're just going to say Chris Pratt. Okay? What was it? Oh, and look at you go. All right, so he's got the hat, and he did the thing where he's like, settle down, Raptor, okay, which totally works completely fine in real life. I'm now going to attempt to draw Raptor. Oh, not doing terrible. Looks a very happy Raptor.
Wait, that's actually like.
It's not the worst thing, right?
It's actually kind of good.
I mean, it's not great. Don't give me good. I don't think I should get good. This is the Barney-esque raptor that has ever existed.
It looks like a dino nugget.
I'm about to eat Chris Pratt. All right, so the raptor begins 25 meters from Chris Pratt. Let's assume that Chris Pratt got a head start, and so he accelerated to his max speed, but we're not going to worry about that. He's already at max speed. When he's at max speed, the raptor notices and takes off, and he will absolutely eat Chris Pratt. Okay, logistically, this was going to happen. Chris Pratt had movie magic, kind of defending him, but it's not the case in real life. The raptor's going to eat it. All right. Oh, he needs arms. Let's do. There we go. There we go. He's not going to use the arms, but whatever. All right. 25 meters away from Chris Pratt. Chris Pratt's going to take off at 6 meters per second, which is a decent max speed. Okay, that's his max speed, running away. And the raptor will start from rest and accelerate at 4 meters per second squared. So let's go. We've got Chris Pratt and a Raptor. What's true of Chris Pratt's motion that we should probably take into account?
Starting velocity.
Remember I said we're going to start when he's already at max speed.
Oh, okay.
So, constant velocity.
Yeah.
Let's go velocity of Chris, time of Chris, displacement of Chris. And the Raptor's motion?
It did start.
Started at 0, so probably means they have to accelerate here. So we'll put all the variables here. Displacement of time of Raptor, displacement of Raptor. All right, what do I know? I said he was running at 6 meters a second. Agreed.
You said he accelerated at 4.
The Raptor accelerated at 4 meters per second squared. Okay.
The initial velocity.
The initial velocity. Is it just like, what? Are you making fun of my drawing? It's Will. Don't worry about Will. All right. Once again, what about this problem would clue you into the fact that absolutely we would use a system of equations. What's that?
Wait.
Missing 3.
Yeah.
Not- Just missing, like, not either side being enough. How many variables do we need with a constant velocity? No, we need 2. How many variables do we need here?
3.
Neither has enough information. This lets you know a system of equations, and once you know a system of equations, the first thing that you should look for is relationships. Any relationships that you notice between the variables out there.
Delta T is equal to delta T.
Agreed? Why?
Because they both start at the same time and they're going until they catch each other or whatever.
Oops, I said that poorly. My apologies. Yes. The time of Chris is equal to the time of Raptor. I'm just going to go ahead and call it T so I don't have to worry about that. Why didn't I put that 25 meters on either displacement? Good point.
Yes.
This is where this
No,
picture
Chris
comes
doesn't-
in.
Chris doesn't have to cover that distance.
Well, let's talk about this. Which way is Chris most logical to go?
The opposite direction.
So, drawing a quick picture here, is his displacement going to be 25 meters?
No.
It might be, but we don't know that it is. Okay, next, is the Raptor's displacement 25 meters?
No.
No, because if it was, he would be where Chris left. This is the displacement of Raptor. Hopefully by drawing that very, very simple picture, you can very easily now recognize what the relationship is between those two displacements. What are they?
Delta XR is equal to delta XC plus 25.
Yeah, how far the Raptor goes is going to be however far Chris goes plus 25 meters, which you can see that plus that has to equal that. So let's write that down. The displacement of Raptor is equal to the displacement of Chris plus 25 meters. Now, unlike the last time we did these relationships and I ended with two variables, time and displacement, I no longer have two variables, I have three. The three variables are time, the displacement of Raptor, and the displacement of Chris. I don't know if I asked you the question here. The question is how long before he's eaten. I guess I could ask how far he goes before he's eaten, but you get the idea. I'm either asking for time or I'm asking for displacement of Chris. Okay, so here is my first equation. But if I have three unknowns, what do I need? Three equations. And we already have one, which got from relationship. Where am I probably going to go for another one? What's that? Yeah, the constant velocity one, because there's only one equation. So let's start over here with Chris. Displacement equals velocity times time, and plug in. This would be the displacement specifically of Chris, and would be equal to 6 meters per second times time. Now I got two equations. Why can't I be done? Because there are three variables. Yes. Displacement of Chris, displacement is not its only variable, they're different. So I need a third equation. Where am I going to probably go for the third equation? We have looked at the relationships. We looked at Chris. So the Raptor. Now the Raptor, of course, has acceleration variables, so there's 4 possible options. So how do you choose the right one? Well, you choose the 2 that you know, and where are our 2 variables? Time and displacement of Raptor. So which equation has those 4? Well, we've already done this one, same one as before. Now, whenever I do this, I always get a little bit weary. And the reason I get weary is because students see me use the exact same equation and they go, oh, I always use that equation. So let me put a small pause on this. I'm going to use a different color entirely because you don't even need to write this down, but I want to show you. What if this problem was different? If the problem, instead of telling you that his acceleration was 4, let's say I told you he hit his max speed the moment he caught Chris, and his max speed was 20 meters per second. If that was your set of variables, would you use this equation? No. Which equation would you use in that case? Which is? And you would plug in, and again, right now, if you were floored by the math, if the math is what's destroying you here, remember I said 80% of it is literally just plugging in here. But let's go back and finish that problem as we had it a second ago. Go back to where it actually is. Yellow here. Okay, yellow, move back here. Get rid of this guy. Come on, get rid of it. Nope, nope, there you go. Okay, so this is 4 meters per second squared. And plug in. This is delta x of Raptor. What's the velocity initial of the Raptor? 0. It's equal 1/2. What's the acceleration of the Raptor?
4 meters per second squared.
Times time squared. And again, there are my 3 equations with 3 unknowns. That's going to net you 80-90% of the points that you would need here. But we will try to finish this real quick. And the reason is because I want you to practice, and I want to show you one last thing, and it's this. Okay, delta x is solved for, delta x is solved for, so I'm going to use these 2 to substitute right in there. What is delta xr equal to? So 2 meters per second squared times time squared, okay, equals, what's delta xc equal to? It'd be amazing if I could stop there, but sadly I do have to add 25 meters. You remember when I told you one time that there's a way to kind of get around the quadratic, and we showed you that way you can solve for velocity first, and I said sometimes you're going to get a quadratic that you cannot get around.
That's this one.
Ta-da! Here we are. So real quick reminder on quadratic here. We know it's quadratic because we have t squared, we have t, and we have nothing else. What is the first step that you should do with a quadratic?
Put the t squared.
What's that?
Subtract the -2.
I'm going to say that a little bit differently, just generically set it equal to 0. And the reason I'm going to do this is actually it's a little bit cleaner, actually weirdly, to move these two. So I'm going to subtract them on both sides. Behold the power of the whiteboard. What I'm going to put in red, I will tell you right now, I do not require, but I would suggest for some of you. And when would I suggest it? If you are looking at this process like it is a foreign language, you want to do as many steps to show you what you need to do. The first one is to remember that this is the generic format of the quadratic. The next is if you want to start going, okay, that means A is 2 meters per second squared, B is -6 meters per second, and C is -25 meters. Anything in red up here, I do not require. Then the next one is writing down the formula, -b plus or minus the square root of b squared minus 4ac all over 2a. Notice I keep writing, you do not have to write this. The only time you would write this is if you know that you were going to make mistakes if you don't. The last thing I would require is simply plugging in. This is -6 meters plus or minus the square root of -6 meters squared minus 4 times, I think it was negative, nope, it was 2 meters per second squared times c is -25 meters all over 2 times a. First thing that you should plug in is all this square root nonsense. That would be 6 squared or 36. The negatives will cancel here. I square root the whole thing, and I get everything underneath the square root is 4 meters per second. Just a reminder when you do this is solving for time. Does negative time mean anything to us? So if you recognize that, you might notice that 6 minus 15.4 is going to get you a negative over a positive will get you a negative, so skip it, don't do it. But 6 plus 15.4 is 21.4 divided by 4 is going to end up with 5.34 seconds. And that's how long Chris has. If I wanted to know how far Chris went, the only thing I would do different is
Plug that into
multiply that by 6, plugging in the original equation, I'd find that Chris made it 32.1 meters. And if I plugged it into this guy right here, oh, I don't get the same number. I get 57.
what? Oh, because
Why am I don't get the same number?
you added 25.
And if you take 32 plus 25, you'll notice it's not quite perfect. Why is it probably not
Error.
perfect? Not error.
You rounded.
Rounded in the setup. If you don't round, you'll get it perfectly every single time. Okay. I always feel like I have to have like more of an emotional conversation with students during this lesson than the actual lesson itself. Okay. Be wary of the phrase honor student. Okay, what it leads you to sometimes is thinking you're smart or dumb or whatever. You are not. You are however smart you are. Your goal in this class is not to show that you're smart or be smart or whatever. It's to grow. My concern with what happened earlier, okay, and I know it happens, I see it happen every year, you're not alone in this, but sadly your education sets you up to believe that if you don't have it in 5 minutes, then you must be an idiot. And that's dumb because this is hard. If you have an emotional response, it's something you need to work on. It will be a process because if you do that, like I said, your brain will go into fight or flight and you won't learn jack squat. Some of you are tired. Don't blame you. It's the end of the day. I get it. But also, some of you just got tired because you let your emotions take over and your cortisol spiked, and it forced you basically into flight, which was get rid of these emotions by going to sleep. And so now you don't know as much as you potentially should. Keep this in mind. This class is about growing. When you forget that and you're like, I'm smart, I'm dumb, you will not learn. You will shut down, and you're not going to learn, and then you will be dumber than you would have otherwise. So be wary of those emotions. Off you go.